the purpose of this video is to teach you how to use percent by mass or combustion data to determine the empirical formula for a compound. By way of review, the empirical formula for a compound is the lowest whole number ratio of elements in a compound. So for instance, C6H12O6 and CH2O both have the same empirical formula. In fact, CH2O is the empirical formula for C6H12O6. The elements are in a 1 to 2 to 1 ratio. When we're working with empirical formulas and percent by mass or combustion data, one key thing to remember is that a mass ratio is not the same thing as a mole ratio. If we consider the formula for water, H2O, implies that there are 2 moles of hydrogen for every 1 mole of oxygen. Bear in mind, this does not say that there are 2 grams of hydrogen for every 1 gram of oxygen. That's because hydrogen atoms and oxygen atoms have different masses. In fact, if we were to use the periodic table, we could see that 2 moles of hydrogen is about 2 grams of hydrogen, and 1 mole of oxygen is about 16 grams of oxygen. That'll give us a molar mass for water of 18 grams per mole. And using this, actually, we can see that of the 18 grams per mole of water, 2 of that is hydrogen. That's about 11%, 2 over 18. And 16 of those 18 grams per mole are oxygen. That's about 89% by mass. So clearly, the ratio of mass and the ratio of moles is not the same, but they are related, and we can use that to find a mole ratio from a mass ratio. Let's see what that might look like. In this problem, we're told that a compound is composed of only nitrogen, hydrogen, and oxygen, and we're given that the percent by mass of nitrogen is 35% and hydrogen is 5%. Since it's also made of oxygen and there's 60% left over, we also know that this is 60% by mass oxygen. What we have here is a mass ratio, and I'd like to turn this mass ratio into a mole ratio for my formula. When working with percentages, it's best sometimes to assume a total sample mass of 100 grams. So 100 grams of my compound, CPD, and we know that of those 100 grams, 35 grams will be nitrogen, 5 grams will be hydrogen, and 60 grams will be oxygen. If I consult the periodic table, I know that 35 grams of nitrogen, multiply that by 1 mole for every 14 grams, and that's going to give me 2.5 moles of nitrogen. Similarly for hydrogen, 1 gram for every 1 mole, and I'll get 5 moles of hydrogen. And then doing this for oxygen, 1 mole for every 16 grams of oxygen, and I find that this is 3.75 moles of oxygen. Now let's take a look at what this mole ratio will give us in terms of a formula. When I write this formula, I would get N 2.5, H 5, and O 3.75. While this is indeed a mole ratio, it's not simplified. And so to simplify this, you don't realize this, but when you simplify a fraction, often what you're doing is simply dividing by the smallest number in the ratio. And when I do this, I get a ratio of N H2O 1.5. Again, we don't have a whole number ratio, but if I look closely, this appears to be 1 nitrogen for every 2 hydrogens and 1.5 oxygens. So I'll simply multiply this through by 2 to double the ratio, and I get N2H4O3. And lo and behold, when I started this, I was using ammonium nitrate as my compound, and I solved for the percent by masses that we started with. we've gone from a mass ratio of 35% nitrogen, 5% hydrogen, and 60% oxygen to a mole ratio of 2 moles of nitrogen for every 4 moles of hydrogen and 3 moles of oxygen. Let's take this one step further and look at some combustion data and see how we can use combustion data to find the empirical formula for a hydrocarbon. Alright, here we're told a compound is known to be composed of only carbon, hydrogen, and oxygen. We analyze that compound by combustion. We burn a 7.5 gram sample of the compound, and we're forming 17.07 grams of carbon dioxide, 6.982 grams of water. And we want to know what's the empirical formula of the unknown. To be clear, we're taking an unknown sample and reacting it with oxygen. That's the combustion. The products of that combustion reaction are carbon dioxide and water. And we can collect the water. A lot of times magnesium perchlorate is used as something called a drying agent, and it will absorb the water, and the mass change will tell us how much water we've collected. And then we can use something like sodium hydroxide to absorb the carbon dioxide and determine how much carbon dioxide was formed. On the next slide, I've simplified this problem statement, and we'll see where we can go with it. So here I'm illustrating. We take 7.5 grams of some compound containing carbon, hydrogen, and oxygen. We're adding excess oxygen, and we're forming carbon dioxide and water. The key to solving this problem is to realize that all of the carbon in the compound will be part of the carbon dioxide, and all of the hydrogen in the compound will be a part of the water. So we'll use the carbon dioxide and the water to tell us about the compound. Let's deal with that now. So we have 17.07 grams of carbon dioxide. And what I want to know about is the carbon in the carbon dioxide. And if I use the periodic table, I know that for every 44 grams of carbon dioxide, 12 of that will be carbon. And that simply comes from the fact that carbon dioxide has 1 carbon, which is 12 grams per mole, and 2 oxygens, 2 times 16 is 32, for a total of 44 grams, 12 of which was carbon. So in this 17.07 grams of carbon dioxide, 4.66 grams are carbon. And remember, all of that carbon came from our original sample. Similarly, we can look at the 6.982 grams of water. And again, with the water, all of the hydrogen in the water came from my compound. Now you might be wondering why we're ignoring oxygen. If I look back up here, you're actually adding excess oxygen during the combustion. So we're not going to use oxygen here. What we care about is the amount of carbon and the amount of hydrogen, and you'll see in a moment how that relates back to oxygen. So we have 6.982 grams of water times, well, for every 18 grams of water, there are 2 grams of hydrogen. And when I solve this, I find that there will be 0.78 grams of hydrogen in that water. Remember, I initially had 7.50 grams of a compound, and of that, 4.66 grams were carbon, and 0.78 grams were hydrogen, and I can find that I'm missing 2.06 grams of oxygen. So at this point, I actually have a mass ratio. I know that there are 4.66 grams of carbon, there are 0.78 grams of hydrogen, and in that 7.5 grams of compound, I also have 2.06 grams of oxygen. 4.66 grams of carbon times 1 mole for every 12 grams of carbon gives me 0.388 moles of carbon. 0.78 grams of hydrogen times 1 mole for every 1 gram of hydrogen gives me 0.78 moles of hydrogen. I didn't even use my calculator that time. And finally, 2.06 grams of oxygen times 1 mole for every 16 grams of oxygen will give me 0.129 moles of oxygen. Now I can take this information and I can write an empirical formula, C.388, H.78, and O.129. That's a lowest ratio, but it's not whole number, so I'll divide by the smallest number in my formula and see what happens. 0.129 divided by 0.129, and this ratio simplifies to C3H6O. If you actually carry out this calculation, you'll see that I get C3.06 something. And if you get a number near a whole number, you can generally assume that that's like a C3H6O. When you get fractions like 6.33, well, you can recognize that decimal as 6 1/3, and you would probably say, well, let me triple this empirical formula to see what I get to get rid of those pesky decimals.